Lab 2 motion of projectile. So for our introduction, we recorded and analyzed a trajectory of a paper ball thrown in front of a whiteboard. So the purpose of the lab was to make a video of projectile object, track its points, and analyze the motion. We used the fundamental principles of kinematics, Newton's first law, Newton's second law, and drag force equation. And the result of running the glow script was actually it was similar to our observed data from Tracker. Ideas of this lab, we analyzed constant force, projectile force with kinematics, which is the study of motion, and then we used these main equations: Vf equals Vi plus F net over m times change of time, and Rf equals Ri plus V average times time, and then the drag formula, which is this B is a drag coefficient, and then you have V squared, which is the magnitude, and then the unit vector of velocity for the direction. So drag force was originally not accounted for, but the motion was not constant due to Newton's second law, because we could see that when we introduced drag force, the glow script code line more similarly represented the observed line, so we knew there was another force acting on the object due to Newton's second law. We chose a scatter and a line of best fit to accurately depict the motion, as it would allow us to see how the object moved over time. And as you can see, this is our trajectory graph, with the blue being our tracker points and the yellow being, and the bottom one, the yellow being our predicted drag with drag. And then for the top one, the red is our predicted drag, and that's closer than our actual just straight glow script code, which you can see. So we have assumed the F drag coefficient to be 0.0035, since it best resembled our observed data, and net force was estimated to be Fg in the first attempt, and then Fg plus F drag when we included drag. For our system and surroundings, the system was a meter stick, a whiteboard, and the force of the toss, gravity, and air resistance / drag. This is our video. Bang. And then these all played into the motion of the paper ball, which we're analyzing. And then, as you can see, our position wasn't exactly 0, 0, but we did account, like our initial position was not exactly 0, 0, but we did account for that. So, initial conditions, we had a paper ball with a radius about 0.035 meters and a mass about 0.002 kilograms. This is our initial velocity and initial position. And again, the goal of the lab was to toss a ball, analyze the points in tracker, put the tracker data in the scatter plot, and then find the initial velocity code into glow script, and then analyze the two tracker plots and then glow script plots. And this is a image of our trajectory. These are other graphs from glow script. So as you can see, this is our code. We have our F drag, calculating that. We have F net force, which is gravity plus drag. And then we had the actual delta iterating the time and the trail. And down here we have arrow scales. The arrow scales I chose were because some were too big and you couldn't see the image, so I just played with those until we found something that was visually appealing and you could still understand the main physics behind it. For analysis and conclusion, the glow script line closely resembled the tracker line, and the slope represents change in meters over a certain time, which is the velocity. So we have our position versus time and our y position versus time. And as you can see, the yellow closely resembles the observed, and then in the position time is actually even better. Our position versus time graph and trajectory graph wasn't exactly perfect to the observed data, but this could come from error like unorganized tracking, wrong drag coefficient, maybe a poor estimation of our initial velocity, and then maybe even a bad starting position that we concluded. No models actually predict terminal velocity because the object never has forces directly opposing each other, as you can see from the glow script animation, but a better experiment would be drop the fall from like a high height and then determine its max velocity, because then you would have gravity directly opposing air resistance / drag. And what if our time would be longer if you throw it straight up, because it must take time to decelerate to zero velocity at its peak, and that would take longer than just tossing it due to this equation. Citations.